Hi, my name is Nitin, and today we are going to talk about Graph Convolutional Networks, GCN. We are going to implement this paper called Semi-Supervised Classification with Graph Convolutional Networks by Thomas Kipf and Max Welling. So this paper came in 2017 at ICLR. So what we'll be going to do is we will implement this paper spelled out, scratch, without using any library. For example, we will not be using any PyTorch Geometric, or we will be not using DGL. Okay. So what I'll be doing is that we'll understand what this equation is. So basically, this is the one layer equation for GCN, right? Next, so I'm not going to do the complete math part. Next, what we'll do is we'll understand this equation, and finally we'll create a two-layer network to implement GCN. We will be doing it on the Cora dataset, so which is defined here. More about the dataset part later, right? And then what we'll be doing, one more thing is this part. So this paper as a supplementary, as an extra part, which basically talks about the how powerful GCN is with in terms of node embeddings with random weights. So we'll be doing this as well. Okay, I have already made this notebook here in GitHub. It's called Spelled Out Intro to Graph Convolutional Networks with my handle Nitin Nilesh, right? And what we'll be doing is that we will be going through this notebook, basically, which contains the implementation. This is basically an image showing how different normalization trick works for GCN, which we'll be covering as well, right? And yeah, like I said, we'll be doing how powerful the node embeddings are with just a random weight, just a single pass. Okay, so let's start. So first of all, this is the blog. This is the blog written by the author itself, Graph Convolutional Networks, right? You can see Thomas Kipf, and this is a very helpful blog. You can go ahead and check. He has written a very intuitive style blog where it's easily understandable, right? And then Thomas has also provided the code. I think it's written in TensorFlow. So yeah, so what we'll be doing basically is we will implement this paper, right, in PyTorch from scratch, and we'll build the intuition how it works, and then we'll see how it goes. Okay, so what I'll be doing is I have created a empty notebook, right? And yeah, let's start. So first thing first, we will start with inputting our all libraries, right? So give me a moment. So yeah, first thing what I'll be doing is, okay, I'm installing PyTorch Geometric. Okay, I told you not to use that. I'll not be going to use PyTorch Geometric, but I'm just doing it to get the Cora dataset. It's very easy. It's inbuilt in this PyTorch Geometric. So I'm just installing it so that I can use the Cora dataset from this PyTorch Geometric, and that's the only use I'll be making of this library. Okay, nice. So create a new code cell, right? And let's import everything. So it says done, right? So we'll be importing NumPy and all the torch part, right? Matplotlib for plotting purposes. Yeah, we'll be using the Karate Club dataset to show the node embedding powerfulness, right? And then we are using the Cora dataset, which is basically a part of the planetoid, right? And yeah, other torch functionalities, and finally we'll be using NetworkX to plot the graph as well. Okay, so move ahead. So first thing first, I want to tell you what graph convolution is. So basically I am assuming that you know what a convolution is in general, the case of images, right? So basically you have an image, and then you have a defined filter kernel size, right? And then you do a convolution, and the idea of doing convolution is that you get the features out of the images, right? But in this case, convolution on graph is different. The thing is, we have nodes and edges, right? And it's basically in the non-Euclidean space, right? because image is in the Euclidean space and this is a non-Euclidean space. So we can't apply the convolution the same way we apply on images, and this is a bit different. Okay, so that's the main idea. So yeah, so first what I'll do is I'll create a dummy graph, right? Just to explain you what a graph data structure is, like how a graph looks like, what is basically nodes, what is edges, what is adjacency metrics, what is the degree of a node and everything. Okay, so what I'll be doing is I'll create a dummy graph using this. So what I'm simply doing, first I'm defining the adjacency matrix of the graph, right? And I'll come to this later, how this is defined. And I'm using network X. Basically, I'm saying network X that from this NumPy array, given this adjacency matrix, can you create a graph? So G is equal to an extract from NumPy array will give us the graph. And then this network X has very good properties that you can call number of nodes, number of edges, and you can get everything, right? So let's see. And I finally used a matplotlib code just to show how this looks like. So yeah, let's see this in action. Yeah, okay. So we can see we have created a graph. So number of nodes in this graph is 6, right? Number of edges are 9, we can see. And this is the adjacency matrix of the graph. So let's understand the adjacency matrix in detail. So we have total 6 nodes, right? And I have labeled them from 0 till 5, right? So this first row, this basically says that node 0 is connected to which other nodes, and the way this is ordered is like 0, 1, 2, 3, 4, 5 and 0, 1, 2, 3, 4, 5. So it's a symmetric matrix, right? Because the graph is undirected, right? It's a symmetric matrix, and all the entries which is 1, which means 2 nodes are connected, and 0 means 2 nodes are not connected. This also conveys the idea that this graph is unweighted as well. So for this video, I'll be assuming that with the GCN we're applying on is basically unweighted and undirected as well. Okay, so yeah, for the node 0, it's connected to node 1, node 3 and node 5. We can see that 0 is connected to node 1, node 3 and node 5. Node 1 is connected to 0, 2, 3, 4. So 1 is connected to 0 and then 2 and then 3 and then 4. So this is basically how the adjacency matrix looks like, and this is one way to represent the graph data structure. You can also use adjacency list, right? Basically, which shows that it's a kind of a linked list structure where each node will just connect it to which nodes which is connected to, right? So there is another way to represent graph data structure as well, but for GCN implementation, we'll stick to our adjacency matrix here, because adjacency matrix give us a lot many information. Otherwise, in general, not be taken from the adjacency list. Okay, so we'll be sticking on adjacency matrix. Okay, so this is our graph. It has this many nodes and this many edges. Okay, moving ahead, what I want to do is the idea is for GCN is that let's assume we have a data set, right? This data set has, let's say, 6 samples. Okay, why I'm saying 6 samples is mainly because I have created a 6 node data graph, right? So each node is basically treated as a sample. So GCN, just to give you an overview, GCN can be used to solve multiple downstream task problem. For example, one of the problem is graph classification itself. So for example, given multiple graphs, can you classify the graphs into different classes, right? Another problem is something called node classification. So given one graph and you have multiple nodes in the graph, can you classify each of the node itself, which class it belongs to? Another problem that you can choose upon this is link classification, right? So, or basically edge classification. So given a set of edges, what classes edges belong to, right? So these are the multiple problems. Today we will be only discussing on the node classification problem, right? And the assumption here is that you can think of nodes as your samples, right? So let's say you have a data set which contains basically, let's say, 6 samples, right? And then each of the 6 samples you have some feature vector, right? and then for each sample you have a ground truth as well. So it's again supervised learning problem only, but the samples are connected to each other in one way, right? And we will be leveraging this advantage to basically maximize our accuracy, right? So it's basically you can use normal MLP as well to solve this problem, but in MLP we just assume that all the samples are independent, are not related to each other. But in graph convolutional networks, we are assuming that the samples are connected to each other, and the way they are connected is defined by the adjacency matrix, right? So yeah, and there's one more thing in this paper which is called semi-supervised. So what basically it means that we don't have labels for all the nodes that we have, right? We do have the connection information between them, but what we don't have is the label information for all the training samples that we have. So that's in general means semi-supervised classification problem, right? Okay, so let's go ahead, and because each node is basically a sample, each node has its own feature vector as well, right? And then correspondingly we have a label as well. So what I'll be doing, because it's a dummy graph, we'll be creating a dummy feature vector as well. So what I can do is that I can say x dot np dot random, right? Random dot np dot random dot random, right? And then what I'll be doing is that simply a number of nodes. So the number of nodes, so 6 nodes we have, and I'm creating a it's by choice, I'm creating a 3 length feature vector, right? And because I'm just rounding it because I don't want to be too big feature vector, so x equal to np dot round, right? So what this does, it creates so let's say number of nodes is 6, so it creates a 6 cross 3 feature vector, which basically shows that for each node we have correspondingly 3-dimensional feature vector, right? And let's print our x and print the shape of it as well, right? So yeah, sorry, np dot round, I missed one thing, I wanted 2. Yeah, so this is 6,3, right? So for each node there is a feature vector, and now you can think of it as one sample basically. Okay, so we have created our feature vector, right? And now the next what we'll be doing, we'll be understanding and explaining this particular formula, what basically proposed by Thomas, right? What we can do, okay, let's start with this. So this is basically the same, right? So this means that for the next layer output, so h is the next layer output for L plus 1, what you need to do is you take the adjacency matrix A, right? And this D is the degree matrix, so I'll come what degree matrix is, right? And this is the previous layer output, and when the L is basically 1, right, or for the initial layer, for the input layer, this h is nothing but x, the feature vector that we just generated, multiplied with some weights, which we will essentially fine tune to get the results. So we'll be implementing this, right? One more thing, it's a tilde. So a tilde simply means that a plus in, and I'll be explaining why a plus in is needed, also why this complicated from where this complicated formula came. Okay, so I'm telling you this, nothing, this formula is no complicated at all, it's very easy formula, right? And then because as we build as we go, you will see that how all this makes sense. Okay, so yeah, let's start with this. So what I'll first start with, I'll simply start with a and then the first layer input, which is nothing but x. So if you come to this formula here, right? Yeah, come to this formula here, right? So this is a 2-layer graph convolution network. So I'll be taking a and then multiplying with x, and finally then multiplying with w. This is the first layer, applying ReLU, and then doing the same process again, finally applying a softmax because of the classification problem, right? So let's start with ax first. Let's see what ax gives us. Okay, So what I'll be doing is, so let's do, just take AX, print, so let's just print, and then let's take our adjacency matrix ADJ and then multiply it with X. Let's see what we get. So we get something, okay? And let's try to understand this, okay? So generally what happens in graph convolution network, when you're trying to update a graph feature vector, so generally what MLP does, right? It takes your input feature vector and then applies some kind of a projection using the W matrix, and then you are in a different space now, like in the hidden layer space, right? Where basically you take it's basically transformed, right? So this adjacency at the time X is basically to understand how the connections between the samples is going to span out when we are updating the node, right? Okay, so let's take this adjacency and then multiply it with X, and what it will do is that for all the nodes, let's say for node 0, it's connected to 1, 3 and 5. So it will aggregate the feature vector of 1, 3 and 5 and to update its own feature vector, right? And this, in terms of graph neural networks, we call message passing. So basically 1 has some message, 3 has some message, 5 has some message, and basically we are aggregating these messages and passing to update the feature vector for node 0, right? But okay, let's understand how this is happening. So what I'm going to do, it's basically take this code. So what this is doing is that for I in range num nodes, so in this case the num nodes is 6, right? I am just keeping a variable here res, which is basically to accumulate the results for each of the node, right? And now I'm printing that this node I is connected to which all other nodes, right? And G is our matrix, so G is our graph here, and Gi dot keys basically gives us for all the nodes the node I is connected to. So for n in Gi dot keys, what I simply need to do is x of n. So x of n will basically give the feature vector for the nth node, right? And add it to the result, right? So when we run this, we'll get something like this. So we see node 0 is connected to node 1, and this is the node 1 feature vector, right? And then node 0 is connected to node 3, this is the feature vector for node 3, and then node 0 is connected to node 5, this is the feature vector for node 5. And when we sum all these feature vectors, like sum of the connected neighbors, we get something 0.58 minus 0.78 and 3.4. And you'll see this is exactly the value what node 0 get after the update when we multiplied adjacency with the X. So what adjacency and X multiplication is doing the same thing, is that for all the neighbors it is connected to, it's just taking all the values, like aggregating all the values and doing a normal sum, right? You can verify for the same as well, like node 1 is connected to node 0, 2, 3, 4, right? And when we sum all this up, we'll get this particular value, which is nothing but the second row. Okay, and this is called message passing in general. Okay, nice. So in this formula, we understood what AX is doing, right? And don't worry, I'll come to this A tilde part. So for now, we'll understood the AX part of this GCN formula. Okay, so yeah, let's go ahead, and what I'll be doing is I want to show what are the problems right now we are facing when we are doing simply A times X, right? So there are two problems. The first problem is node 0 is connected to node 1, 3 and 5, right? And it's taking the sum of all its connected neighbors, but it's not taking the feature vector of itself, which is the most important one, right? So this is one of the problem, is that node 0 is taking the feature from node 1, node 3 and node 5, but it's not taking the feature vector of node 0 itself. So this is one of the problem, clearly. The second problem that we're encountering is that when we are doing the aggregation, it's a normal sum, which means the features which are being aggregated are not normalized, right? So we will see these two features together, that these two problems together, and then how to solve these two problems. Okay, so let's solve the first problem, that the node itself is not, the node is not taking the feature vector connected to itself, and it's taking the all other feature vector. And this can simply be solved by adding a self loop to the graph. So if I add a self loop to the graph, that node 0 is connected to itself, then it will aggregate its own feature vector as well, right? Okay, so let's go ahead and do that. So what I'll be going to do is that simple idea is that I can say adjacency loop is nothing but adjacency plus add identity matrix, right, with of identity matrix of size n, right? So that you simply take the adjacency matrix and you add identity matrix, right? What it will do for each of the node itself, it will add a 1, right? Okay, so this is adjacency loop, and let's now print this. So print the graph, and let's print the self loop as well, right? Yeah. So now this is the adjacency matrix, which is now transformed, and you see all the diagonals are 1, which simply means that the node is connected to itself. And when we plotted the graph, we can see now there is a self loop. So 1 is connected to itself, 2 is connected to itself, and all the other nodes are connected to itself, right? And now let's do the same thing again. Let's, instead of doing a times x, let's do adjacency like a tilde. Let's call it the self loop adjacency matrix as a tilde. So we'll be doing a tilde times x, so that now we are adding its own feature vector as well. Okay, so I'll be writing the same code here again, right? So a tilde x is basically, now see it has changed, and now it's saying that node 0 is connected to node 0 itself, right? Node 1, node 3, and node 5, and now it's doing the sum, and this sum is nothing but the first row, which basically belongs to node 0, right? And then a node 1, it's saying node 1 is connected to node 0, node 1, node 2, node 3, and node 4, and the sum of these numbers are minus 1.88, 1.27, and 0.7, which is basically the second row, which corresponds to node 1. Okay, so now we understand this part of this equation, that when it says a tilde is d to the power minus 1 by 2, a tilde d to the power minus 1 by 2, we understand what is the a tilde part, but still our a is not complete yet, and this will be completed when we will solve our second problem, which basically says that the sum of aggregated neighbors are not normalized. Okay, so let's go ahead and solve this problem as well, solve the second problem. So what are the ways we can normalize? So one way to normalize, it simply take the mean, right? And how can we take the mean in this case? So to take the mean, what we'll simply do is to use our degree matrix. What is a degree matrix? So degree of a node is a number which basically shows to how many nodes it is connected to. So let's say if I come to node number 0, so 0 is connected to itself, 1, 3, and 5. So it's connected to 4 different nodes, right? 0, 1, 3, and 5. So the degree for node 0 is 4. Let's say I come to the node 1. So node 1 is connected to itself, right? It's connected to 2, it's connected to 3, it's connected to 4. So it's connected to 4 nodes, and the degree of this node is 4. And similarly, we can include the degree for all the other nodes. And it's basically, when you compute the degree matrix, it's basically a diagonal matrix, right? Where each other diagonal is showing that how many, what is the degree of each of the node we have, right? And that's the matrix D, degree. And given the adjacency matrix, finding the degree matrix is very easy. So for any given node, let's say we're talking about node 0, if we simply sum up this node, right, which will give us 1, 2, 3, 4, which is basically the degree of this node, right? So a simple sum, like a row wise sum or a column wise sum, will give us the same degree matrix, because it's a symmetric matrix. Whether you do it row wise or you do it column wise, it does not matter. Okay, so let's go ahead and create our degree matrix. All right, so what I'll be doing is we can simply write d is equal to np dot sum, right? And let's take this adjacency loop, and then x is equal to 1. Doesn't matter what x's you take here, right? And now you can let's print this d, right? So you see 4 5 3 5 3 4. So node 0 is connected to 4 different nodes, node 1 is connected to 5 different nodes, right? And it's for now it's not a diagonal matrix, but we'll be converting it to diagonal matrix, right? So now we got our degree matrix, right? Now the case is how do we mean the features that we got? And one of the ideas is that because we got this number which is connected to, if we simply divide the features by this number, we will be getting this mean aggregated feature vectors, right? So what I simply need to do is that if I simply do d to the power minus 1, right, I will get this feature vector, which basically get the mean value of it, the number from which we should be dividing to, right? So if I just say, I'll call it this variable norm. So if I just say norm is equal to np dot, so what I can do is simply d to the power minus 1, d to the power minus 1, right? And what I can do is I can call np dot diag to make it as a diagonal matrix, right? np dot diag. And now what I can do is then I can multiply this with adjacency loop, right? I think this is fine. Yeah, and then let's now print the norm. So this norm is basically contains the aggregated feature vector, right? Okay, it's great. Now these are all I can say normalized. Yeah, this is the way. So you see, because let's print the d once more, right? Right. So see, this is 4. This is 4. So 1 by 4, 0.25, 0.25, 0.25, 0.25, from where it is all connected to. So now this can be seen as our adjacency matrix, right? So this is the weightage is to given to the connected nodes, the neighboring nodes, right? And I'm calling it norm. Okay, but and let's see that how importance is given. So what I'm doing, I have created a matplotlib code, utility code, so to basically show yeah, how this looks like. Yeah, this is very good. This is the graph showing importance of nodes with respect to node 1, right? And we can see that node 1 is giving importance to node 0, 1, 2, 3 and 4, and it's everywhere same importance, right? So this is good, this is not a problem. But in GCN paper, Thomas came up with a renormalization trick, an extra trick. And what basically Thomas suggesting is that instead of doing I plus d to the power minus 1 by 2, a to the power minus 2, what we can do simply is that let's take d to the power minus 1 by 2, a tilde d to the power minus 1 by 2, where a is a plus in, right? So we have already this a, which is a plus in, right? And then what we are doing is that taking d to the power minus, so d is the degree matrix, and d tilde simply means the degree matrix for the adjacency loop, right, where the self loop is there. So d to the power minus 1 by 2 times the adjacency, and then d to the power minus 1 by 2, right? And this will give us this will give us this one, basically one forward pass, one layer, right, of the GCN. Okay, so let's see. So this is one way to d to the power minus 1 by 2, a to the power 1 by 2 times x is basically one way to normalize the feature vector. Okay, so let's do this and we will see how it goes. Okay, Yeah. So what I'm going to do is yes. So now you see, I'm simply doing np.dag d to the power minus 1 by 2 times a tilde times np.dag d to the power minus 1 by 2, right? And this will give us n cross n matrix, right? So now you can see this is the mean normalization and this is the normalization using the renormalization trick. And we can see, let's try to understand this, okay? So if you see from the node 0 itself, all the nodes are not given the same importance. Now we can see there's a difference in the importance, right? And it's better if you see it from the graph point of view. So let me plot another graph, right? Okay, this is much better. Yeah. So if you use the mean normalization and if you're seeing the node with respect to 1, so 1 is giving same importance to all the other nodes. However, with the renormalization trick, you see, okay, so the lighter the color is, the lower the weightage is, and the more yellowish is more the weight. So you see, 1 is giving much higher weight to 2 and 4, and then it is giving lesser weight to 3, and then much lesser weight to so it's giving lesser weight to 0, I'm sorry, and then much lesser weight to 1 itself and 3. And now try to understand what this normalization trick is doing. What it's basically saying is that the nodes which this is connected to, so let's say 1 is connected to 2, right, and 2 is not connected to many other nodes, right? 2 is only connected to 1 and 3. Similarly, if we see 4, 1 is only connected to 4 and 4 is connected to no one else but 4, which means the feature that they will provide is much more solid than rest of the other node features, right? And when I say solid, I simply means that because let's take for example 3 is connected to 2, 1, 0 and 5, right? So this node, when you are updating it, when you're doing the aggregation, is much more diluted. It's taking a feature vector on so many other nodes. However, if you see 2 or 4, it's taking only from it's only connected to 3, right? 2 is only connected to 3 and 1, and 4 is only connected to 1. So the feature vector is going to provide will be much more solid in the case, not diluted, I can say. And if you want to understand this in a better way, there is a blog post by Matthew Bernstein, right? I have opened it here. Yeah, I have opened it here. And Matthew has explained it in a much better way. So I recommend everyone to take a read this blog. And Matthew has, used, this way to show the importance of this renormalization trick, right? That 5 is getting much higher weight and 1 is getting much lower weight, right? If you see the graph here, then 5 is getting much larger weight and 4 is getting much lower weight because 1 is connected to so many other nodes and 5 is only connected to 4, right? Okay, nice. So this is the intuition behind the renormalization trick, that why this kind of aggregation instead of mean normalization is better. Okay, let's go ahead. So what I'm going to do is now let's do message passing. So now we have defined our adjacency matrix, like the normalized adjacency matrix, and now we can see what are the changes the message passing brings to us. Alright, so if this is using unnormalized, simply adjacency times x, and this is using the renormalized, right? Renorm times x, right? So because of the renormalization trick, this will give a better understanding of which node is connected to which node, and from which node you should be taking the feature vector, like what is the weightage of each node you should be defining among your connected neighbors. Okay, now what we'll do is we will define one GCN layer, right? So we'll define this whole thing, one GCN layer, right? And in general, what we are trying to implement here is this particular function, right? So we have already defined what is AX, right? We will be defining the first layer, ReLU, and then the second layer, and then the softmax. Okay, and this we will be doing in NumPy for the beginning, right? And then when we understand using the NumPy, then we will go to the PyTorch, right? And we'll do the same thing in PyTorch, and we are using PyTorch just to get the advantage of AutoGrad so that we can train it end to end. Okay, so let's do it. So before we go ahead, let's understand the shape and everything, right? So I'm defining a seed here so that you can reproduce the same result as me. And what I want to do is that I'm creating some random labels as well, right? So for each sample we have 6 nodes. Each node is being considered as a sample. So for each sample we are creating a label as well. So I have 6 different labels, right? And for now I'm considering this binary class classification problem. I'm only considering 2 classes, right? Okay, so our adjacency matrix shape is 6 cross 6. The feature matrix shape is 6 cross 3, and then we have 6 different labels for each of the nodes, right? Okay, now let's go ahead. Okay, so let's convert everything into torch tensor, right? So what I'm doing is that simply I'm taking X and converting it into torch tensor, and then I'm converting all my normalized adjacency matrix as torch tensor as well, right? Nice. Okay, so we have X, we have the labels, we have the normalized matrix, and what we need to do, we need to get initialize our W, and then we can write the first layer, and then similarly we can write the second layer as well. Okay, I'm defining layer 1, right? I'm defining layer 1, so I'm making a generator so that the results are reproducible. Okay, and I'm choosing a hyperparameter here is that output dim is 2. So for now our input shape is 6 cross 3. Our X, the feature vector, is 6, 3. 6 samples, each having 3-dimensional feature vector. My when I pass it to one GCN layer, I wanted to project it to 2-dimensional feature vector. So when I'll pass it to the first layer of GCN, I'll get 6 cross 2. Okay, so I'm choosing it's 2. Okay, you can choose it to any other number, it's just my design choice. Okay, next is we'll be creating our W. So for the first layer W, we can define it something like this. So torch dot random, and then input dim, and then output dim, right? So the input dim, output dim, and I'm using this fixed generator. So generator is this fixed generator, right? So this way I'm defining the W1, right? And then I'm defining the bias as well. So which is nothing but torch dot random, and output dim, and then using the same generator again. So generator is fixed generator, right? Okay, let's see. Okay, we got our W and we got our B as well, right? There's one more thing the paper has done while initializing the W's and B's. It made sure that the initialized weights are using the Glorot uniform initialization. So let's go ahead and do that as well. So first let's find out the standard deviation. So let's do this. So let's find out the standard deviation of W, what we got, and then simply take a uniform distribution out of minus standard deviation plus standard deviation, right? So in this way, let's print everything. So let's print, and yeah. So this we got our W1, right? So this is our W1, which is size 3 cross 2, and this is our B1, which is size 2, because our input was 6 cross 3 and this weight is 3 cross 2. When we do the projection, we will get 6 cross 2. Okay, now this is the layer 1 forward pass, right? So now what we'll do is we'll create our layer 1, right, and see how the forward pass is. And now the forward pass is simple. Layer 1 forward pass is simple. We have the adjacency matrix A, like the renormalized, we have X, and we have our W0 as well. And a simple matrix multiplication will give us this thing, right? This particular thing AXW0, right? And when we apply ReLU, it will be our first GCN layer, right? So let's go ahead and do that. So I'll call it message aggregation. Message aggregation is nothing but renorm, and renorm is nothing but the normalized adjacency matrix A, right? And I'm multiplying it with our feature vector X, right? And we have done this before renorm at the rate X, and now multiply it with our weight. So I'm calling it Z. So Z is nothing but message aggregation at the times, I guess it's called W1, right, plus B1, right? And then finally we can pass ReLU, ReLU, right? And then I think we'll get, so this let's print it. So let's print Z, and this is nothing but the output of our first layer, right? Print Z, and let's print shape of Z as well, right? Yeah, okay, so this is Z, this is 6 cross 2, right? And we see zeros here because of the ReLU activation function, and the shape is 6 comma 2. So now, for now, we have implemented till this part, and this is the first layer, right? Next is what we'll be doing is that we'll take this as input, again multiply with our adjacency matrix, the normalized adjacency matrix, and multiplying with our weight, and it will give us the second GCN layer, right? And when we apply a softmax into this, because we are doing a node classification problem, this will give us a 2-layer GCN, right? So one thing, okay, let me first implement it, and then I'll come to the analysis part of it, okay? So what I'm doing here is, similarly, I'm creating layer 2, right? And what I'll be doing is that, again, I'm doing a generator, and I'm choosing output dimension 2 again, right? Because it's a binary class classification problem, I'm choosing the layer 2 output dimension as 2 as well, right? The input dimensional is the output of the Z, the output of the first layer, right? And then I'm creating W again, same way, using a torch.random from input dim to output dim. So this is basically 2 comma 2, bias is 2 comma 1, right? And again, I'm doing a Glorot uniform initialization, right? So simply find out the standard deviation and do uniform, create a uniform distribution between minus standard deviation to the standard deviation, right? And let's see how our W looks like. So in this case, now the W is 2 cross 2 because the input, the output of the first layer was 6 cross 2, and we again want a 2-dimensional feature vector. So I'm creating a 2 cross 2, and the bias is also 2 cross 1. Okay, nice. Now let's do second layer. So second layer, again, straightforward, right? What we can do is simple, renorm at the rate renorm multiplied by Z. So what is Z here? Z is nothing but the output of the first layer multiplying with our A, right? Normalized A, and simply again normalized A, whatever the message we aggregated, multiplied by weight, and then biases, right? Added with biases. Nice. And this is the output of second layer, right? 6 comma 2. So we implemented till this part it is implemented, right? And now we have to apply a softmax. So I'll be using, because it's a binary class classification problem, I'm using PyTorch. I'll be using this cross entropy, and if you go to the PyTorch cross entropy, you'll get to know that PyTorch cross entropy is basically a combination of NLL, the negative log likelihood loss, followed by the softmax. So I'm not explicitly using softmax here, I'm just using the criterion cross entropy loss, which does the softmax for us. Okay, and let's go ahead and yeah, so let's do that. So simply what we can do here is, so the loss is nothing but f dot I think I call cross entropy, right? And the cross entropy loss we need to find out between our out, which is basically the output of our network, right, between the labels y, right? And so this will be our loss. So the loss of 2-layer GCN is 0.7140. Okay, so yeah, what we see here is that we got the loss, and basically we did the forward pass, we found out our loss, and now we have to do the backward pass, right? So because we implemented in PyTorch and we have AutoGrad, we don't need to manually write the backward pass as well. We can simply call loss.backward and it will give us the gradient for each of the weight metrics we have. Okay, so now let's implement our GCN properly this time using classes and everything. Okay, so let's create a class called GCN layer, right, which is nn dot, and then I'm taking nn dot module here, right? And then what I can do is, sorry, so it's taking self, and what it will take, GCN will take that what is the input feature, which is basically what is the number of the feature dimension at the input layer, and how many you want at the output, right? So we'll call it out feed, right? And then what we'll do is, yeah, obviously initialize the constructor as well, right? Super.init. Now taking in feed is in feed, right? So I'm creating the self variable for them, self dot out feed is equal to out feed, right? And now what I need to do is to initialize my weights as well. So because these weights are nothing but a PyTorch linear layer, right? Because you see what we're doing is that given the feature vector, given the input feature vector, we are multiplying with W and then adding a bias, right? So this is nothing but a linear layer. So I'm calling it self.projection, and this is nothing but nn.linear. Self.projection is nn.linear, and this basically in feed and out feed, right? And I'm not worrying about the road uniform initialization here because PyTorch by default does the initialization for us. So nn.linear does the initialization for us. You can go ahead and check the documentation as well, right? So we got our weight matrices initialized as well, right? And now let's time to do the forward pass. So let's do forward. So in forward, what we are assuming, right, that we'll get our x, the input feature, and then we'll get the adjacency matrix. So what we can do basically, instead of computing the a norm each and every time, what you can do, we can pre-compute it. Because the adjacency matrix is fixed for the graph, it's not going to change, and the degree matrices are not going to change. What we can do is that we can pre-compute this norm, right, and save it, so that each time we can simply multiply it to the x, right, and we can simply multiply it to the w as well. You can also pre-compute renorm at the rate x, right, but yeah, it's up to the design choice. What I'm doing here is simply taking the x and multiplying with the predefined a norm. Okay, so simply what we need to do is that we need to do a torch dot matrix multiplication between a underscore norm comma x, right? So this is our this is the message aggregation. Basically you take the adjacency matrix and you multiply it with x, and you multiply it, so you aggregated all the message, right? And then now it's time to multiply it with the weight vector, which is nothing but our projection. So you can simply call it self dot projection and multiply it with x, right? And then return x, right? So this is our forward pass for the first layer, right? And what I'm doing is that I'm also adding a cute representation for this layer. Okay, so basically what this layer means is that so it's a like a inbuilt class function, REPR, which is basically when you call the print, this function will be called, and it wants you to return a string, right? So it's returning, basically I'm using f strings here, that this is a GCN layer, right? This is a GCN layer, which basically has what from input to output, like how many features it's taking. So it's taking self dot in feed and going, so I think this will go in this, yeah, and then we are going to self dot out feed, right? I think this is good, right? So this is one layer, so I can call it, this is a one layer of GCN, one layer of GCN, right? There's one layer of GCN, and now let's build our whole GCN model, right? Class GCN. So let me get this from here because this is straightforward now. So what I'm basically doing is that I'm taking this GCN model, right? And I'm creating two layers. So from one, the first layer is from the in-feed to the number of hidden, and from the number of hidden to number of classes, right? So this needs in-feed, number hidden, and number of classes, and what activation function you are planning to use, and if also you are planning to use dropout or not. Okay, so initialize the two GCN layers, right? And then the forward pass is pretty simple. You do the forward pass for the first layer, apply the activation function. If there is a dropout, then apply dropout, right? And then you apply the second GCN layer, and then you return this. Okay, hopefully I'm not getting any error. Yeah, okay, this looks good. So this, what we have defined, is our one GCN layer, right? The whole GCN model, right? Which basically has two layers, right? And we are using our choice of activation function and whether we want to use dropout or not. Okay, so this was implementation of GCN. This concludes one part of the video, right? Is that how can we simply take this equation, right? So we implemented this whole part, right? And then how GCN is taking care of samples connection using the adjacency metrics, right? How we are doing the renormalization, and how can we use it for classification purposes. Okay, nice. So now it's time to get the dataset, because we have written our model. So this time to get the dataset, and I'm using the Cora dataset, right? On top of that, I am taking the dataset fetch implementation part from this course, GDL course taught by Professor Michael Bronstein, Joan Bruna, Taco Cohen, and Petar. Right? It's a very good course. So if you're interested in geometric deep learning, I highly recommend doing this course. Right? There is a book as well. Right? So what I've done is that I've taken this particular implementation of dataset loading part from this. Okay, so let me do that. Let me go ahead and copy that. Okay, so yeah, so what this is basically doing is that I'm using the planetoid from the PyTorch Geometric to get the Cora dataset, right? And now you see here, this has train mask, validation mask, and test mask, right? So if you see here, let me get the dataset first. If you see here, then we'll see a very interesting phenomena, which is basically, we'll see why it is called semi-supervised learning, right? So I'm downloading it. Okay, and when it is getting downloaded, I'll just do one more thing, is that okay, so I've written this code. I've taken this code, basically is that basically it shows the number of graphs is 1, so it's a Cora dataset. What basically Cora dataset is in a nutshell is that it's a graph, it's a dataset which contains many research papers, right? And for all the research papers, it has used a bag of words kind of technique to create a 1433 dimensional feature vector. Okay, 1433 dimensional feature vector, and we have connections between the samples in such a way. So let's say paper A cites paper B, which means there is a connection between paper A and paper B. And for now, we're defining an undirected connection, which means it's a undirected edge, let's say paper A cites paper B, then there's an H, undirected. Okay. So this is how the dataset has been generated, right? This is how the adjacency matrix has been created, and it has in a total of 7 classes. So all the papers are defined in 7 different classes, right? Total we have 2708 number of samples, right? And we have total somewhat around 10.5k edges. Okay, now the interesting factor of this, out of this 2708 nodes, we will be only using 140 nodes for training purposes when we will be training our this GCN. And that's where the semi-supervised learning part comes into the picture, that we are not simply doing a train test split of 80% or 10%, 10%. We are simply, what we're doing is that we're only taking the 140 samples out of the whole training dataset, and this 140 is coming from 20 multiplied by 7, which simply means for all the 7 classes, for each of the 7 classes, we are taking 20 samples each, right? And then we are making 140 samples. So, and we will see how we will leverage this semi-supervised learning part to train the complete GCN, right? To train it and predict it. Okay, so there's an adjacency matrix we have is 2708 cross 2708 because there are 2708 number of nodes, right? And the X we have for now is 2708 by 1433, right? Like I said, for each node we have a 1433 dimensional feature vector. Okay, the training is 140 nodes, right? Validation is on 500 nodes and test is on 1000 node again. Okay, so this is what the dataset looks like. Okay, now let's go ahead and but yeah, before I go and train the whole GCN part, what I want to do, because GCN and MLP are same in terms of number of parameters they're training upon, right? So if you see closely here, right, what Thomas has done a comparison, very good comparison. Yeah, look at this. So this is our GCN that we are going to implement, right? A to the power minus 1 by 2, a to the power minus 1 by 2, x and theta, where a is the adjacency matrix and d is the degree matrix, x is our feature vector and theta is basically the weights, right? And this is what MLP does. So it takes the x and multiply with the weights. So in terms of parameters that we are learning, it's exactly the same, because there's nothing to learn in A, there's nothing to learn in D, right? There's only thing to learn the theta part. So in terms of parameters, number of parameters, these two models are exactly the same, right? So it would be great to see how MLP works and then how this GCN works, right? Because the number of parameters are the same, it's not changing at all, right? Okay, so what I'll do first is I'll implement an MLP first, right, with 2 layers I believe, and then I'll implementing GCN as well, and we'll see what is the difference between the accuracy. And we are hoping that GCN would work better, ideally because it's connections, it's adjacency, like it's the connection between the samples. So now we know the connection between the samples, which MLP does not know, right? We know the connection between the samples, and we will leverage this to update the feature vector, which essentially what MLP does, right? If you do x times theta, it updates the feature vector, but it assumes that no samples are connected to each other. But in GCN there are sample connection, right? And then what I'll be doing is that seeing how the accuracy changes based on the advantage of sample connections, right? Okay, so let's go ahead and implement MLP first. Okay, so what I have done is I have written a simple MLP code. Yeah, so class MLP, right? So the first layer is an inner linear between in-feed to number of hidden, and the second layer between number to hidden to number of classes, and then I'm also adding a batch norm. Okay, so batch norm is just my implementation. Okay, and then simply take the linear, pass to the first layer, apply activation function, and then pass to the second layer and get the output, right? So this is our MLP. Okay, and now what I'll be doing is let's apply a normal PyTorch boilerplate code for training things. So what I'm doing here is that I'm defining a train function which does nothing but model.train, which basically go to the train part, right? And then optimize.zeroGrad, do a forward pass, and then compute the loss, do the backpropagation, and update the weights, right? So this is the training part. Similarly, this is the evaluating part. Do a forward pass and find out that how many of them are correct, right? And then find out the accuracy. And for some number of epochs, I'll be doing this, and we'll see what is the accuracy we are getting, right? Simple. So first train the MLP, and then evaluate MLP, and then evaluate on the validation data as well, right? And then print some information. This is normal boilerplate code for PyTorch, right? Okay, so yeah, let's start training this GCN first. Sorry, MLP first, right? Okay, we are on CUDA. Nice, thanks to Colab. And I want to do it with 101 epochs. Okay, let's do it for 101 epochs. Okay, and let's train it. So what I'm doing is defining the model here, right? So I'm defining the number of hidden is 16. So I'm going from 1433 to 16, and then finally the second layer is 7 because we have 7 number of classes, right? And then I'm simply training it. So let's train it. Let's see what we get. Okay, so we get somewhat around 50.9, okay, after 100 epochs. So which is somewhat around 51. Not bad, not bad. So MLP, which does not know anything about the connections of the samples, is giving it 51%. Okay, and now we have a baseline. Okay, so now we'll see how do we go ahead and train our GCN model. Okay, let's go ahead. So okay, so there's one thing that I want to focus upon is something called transductive learning versus inductive learning. Okay, so what transductive learning means, so what inductive learning means first is that what we did with MLP is that it takes all the data, all the training data, right, and then some amount of validation data and test data, and train on the training data, and we get the output, right? We get our accuracy on our valid and test data. And this is what simple inductive learning means. What transductive learning does, for example, in this case of GCN, even though we are just using 140 samples for training purposes for GCN, the model can see the whole adjacency matrix. The model is not only showing those 140 nodes, the 140 samples, it's seeing the adjacency matrix for the whole graph, which includes both training and testing as well, right? And it's using the adjacency matrix to update the feature vector for only the training part, not for the other nodes. And because we're using the whole adjacency matrix, this comes as a transductive learning, right? So what we'll do in this case, so let's go ahead and implement this, is so the same training part again, right? So we have model.train, optimize.zeroGrad, and now this time when we are doing x times a, we are doing the forward pass, we are getting only the out for the mask, whether it's a training mask or a validation mask, right? And we are computing the loss only for those samples which are part of the mask. So you see here, that's the transductive learning basically, is that even though like we are taking the whole x and the a, but when we are computing the loss, we are computing the loss only for those 140 samples. Okay, and this is also applied to the validation as well. So we are passing the validation mask here, and the out is only for those masked samples which are part of the validation basically, right? And now when we are calling this, so we are calling this the whole A norm, the whole adjacency matrix, the complete train X, train Y, and we are passing the train mask as well when we are calling this training function, right? And when we are evaluating it, and we are passing the validation mask for the evaluation, right? So now let's train the GCN. Okay, so yeah, so this is the loop. So this is basically the training function that I have defined, and now let's take the data. So I'm getting the data again. It's in symmetrics, the x, and then I'm doing the pre-processing. So I'm doing a is equal to a plus I, and I'm applying my renormalization trick, right? Which is nothing but compute the degree matrix and do d to the power minus 1 by 2 times a times d to the power minus 1 by 2. This is a normalization trick that we saw earlier, right? So we got our data set, and now it's time to train, right? So let's train. So I have written the code for training as well. So simple. Take the model, pass it to the give the input number of features, give the number of hidden layers, again 16. So we are doing the same thing as MLP here, and number of classes is 7. We are using ReLU activation function, right, and using a 0.5 dropout. So I'm taking these numbers and this activation function exactly as what defined in this paper, right? Okay, so let's train it. I'm getting some error. Has no attribute outfit. So I think this is the problem where I defined my GCN, I believe. Let me check my GCN implementation. So it says outfit here. This is correct. Infeed outfit. Infeed outfit is correct. Self.outfit. Right. Oh, what is the problem here? GCN L1, L2. Let's see. Okay. So infeed num hidden, infeed to infeed, outfit to acha. Okay, got it. Wow, what a silly mistake. Yeah, it is equal to here. So right, this is fine. And now what I need to do is need to define my model again and train it. I hope this trains this time. Yeah. Okay. Wow, we are getting somewhat around 79.8% validation accuracy, right? Which is somewhat around 80%, and this is what paper has also claimed as well, right? So GC in this paper on Cora is somewhat around 81.5, right? With plus minus 0.5. So we're getting 80%, somewhat equivalent, normal. Okay, so yeah, so this is how we see that how GCN is much better in terms of applying, taking leverage of the connections between the samples, right? Okay, now next what I'm going to do is that, this part of the paper is this. So what we're going to do now, this is the interesting part, is that we are taking the Karate dataset. I'll explain what Karate dataset is. Okay, and what we're doing, we are creating a 3-layer GCN network, with tan-H activation function. Okay, and the idea here is that so this is the Karate dataset, and this dataset is only defined. It has no feature vectors, right? It has only defined the connections between different classes. So it has 4 different classes, which basically represents the 4 different clubs in this Karate Club network, right? What we are going to do is that we will initialize our feature vector as identity matrix. So this has total, I believe, 34 nodes. This graph has 34 nodes, total 154 edges, right? And then what we will do, and 4 classes, and what we will do is that we will initialize our feature vector with identity matrix, which is nothing but 34 to Cora 34 matrix, right? And number of classes is 4. And we are not going to train this model. What we will do, we'll do a simple forward pass, just one forward pass with random weights. So whatever weights we initialized for the GCN model, we are not going to train it at all. We'll do a normal forward pass, and what we'll do is that whatever the output we have got, whatever the output we have got. So in this case, I think we will get an output of 2, right? 2-dimensional output, the way we have defined the model, and we will try to see what embeddings the model has learned for these, what feature embeddings basically the model has learned, right? After doing the one forward pass. And this will ideally should get like this, where you can see the red samples are here, right? All the blue samples are here, green samples are together, and the purple samples are together. So just one forward pass shows you the power of the GCN, what it can learn basically. Okay, so let's go ahead and implement this. So what I'll do is, so I'm getting the Karate Club dataset from the PyTorch Geometric. Okay, get the adjacency matrix, right? And what we're going to do is that, okay, we're only going to train upon, we're not going to train upon, by the way, we're just going to do a forward pass with the train mask, right? Feature, like I said, it's a identity matrix, so there's no feature at all. It's like a featureless initialization, right? So let's go ahead and see this network, so see this graph. So number of graph is 1, there are 34 nodes, right? 4 classes, number of nodes per samples is 34, obviously, yes, age is 156, and then finally adjacency matrix we have 34 by 34, right? And we are going to only take 4 samples, like 1 sample from each class for training purposes. However, there is no training involved here. We are just going to do a one forward pass, right? Just one forward pass taking these 4 nodes, right? So let's build the model based on what defined here in the paper. Let's go ahead and build this model. Okay, so what I'm doing here is I'm building this model. Okay, so we have this GCN model Karate, right? And I'm defining the 3 layers, right? So the first layer, second layer, and third layer. And I'm doing just one extra implementation here. I'm adding a batch normalization because the weight initialized, just doing a forward pass can go to the any distribution, right? So I'm using batch normalization, so my distributions are following like a Gaussian curve. Okay? So again, in the forward pass, GCN, so the first layer, right, applied by the activation function, followed by the activation function, then batch normalization, the second layer, right, activation function, batch normalization, and finally the third layer, right? So what I'll do is that I'll take the adjacency matrix and I'll do the pre-processing like I'm doing before. I'm doing a plus I, right, and then compute the degree matrix and then doing the renormalization part, right? Okay, so we did, and now let's do just one forward pass, nothing else. Let's just do one forward pass. So we are creating a GCN model. Input is 34, number of hidden is 4, right? So 34 to 4, 4 to 4, and then 4 to 2. So these are the 3 layers. Okay, I'm using a 10H and no dropout, right? I'm just doing a simple one forward pass, nothing else. No training involved in this, just doing a simple forward pass, right? And then whatever output I'm getting, because it's a 2-dimensional output, we can plot it easily in using matplotlib. I'm trying to, wow, look at this. Oh, this is very beautiful. So all the red samples are somewhat together, blue samples are together, green are together, and all the cyan one are together, right? So this is just after one forward pass, we can see that like a identity matrix feature vector is basically transformed in a feature vector where any normal clustering algorithm, you take any normal clustering algorithm, will be easily able to cluster the classes together, right? So this is the power of GCN, right? And this is the one of the important aspect of this paper, that it can be compared to, there's something called WL algorithm on the it's here in the paper, right? The Weiss-Feiler-Lehman algorithm, which basically shows so this algorithm was basically created invented in 1968 just to check the isomorphism between 2 graphs. Don't worry about this. You don't need to go about all this. It's just the idea is that the idea is to show the power of GCN itself. Without doing any training, just one forward pass can give you all this, give a very nice feature vector. Okay, so yeah, I think this is it from this video, right? So what I'm trying to do is that I have implemented a GCN, right from the scratch, just using only PyTorch, right? I've trained it on the Cora dataset, and then basically we understood how the equation spans and how it works exactly, right? What I have not covered in this video is the mathematical concept behind it, because I thought maybe I'll cover it in some other video. The video will go too lengthy and all that. I have not also done something called sparse implementation, because the adjacency metrics mostly contain zeros, right? So you can do a sparse implementation of this whole GCN, but I've not done this in this video because my idea of this, or aim of this video, was just to explain what GCN is, not the sparse variation of GCN. So I hope you understand what GCN is, right? As a final conclusion, what I would like to say is that GCN is great, right, to deal with graph-based dataset, right? But there are some limitations of it. For example, you can't train a deep GCN network, because let's say as you start going ahead, like start creating layer by layer, your one node will start getting features from your k neighborhood, right? And what do I mean by k neighborhood is that, let's say you take a k step walk from your own node, and you will reach to some other node, right? And as you increase the number of layers, you will start getting the updates from the nodes which is in your k neighborhood, and that can be noisy as well, because this node is not connected to the other node by any means, and if it start getting the update, the feature update from the other node, then it can have a problem. So another limitation of GCN is that you can't create a deep GCN network, right? But yeah, given that the GCN itself is powerful enough, like we saw in this part, right? Whatever till now we have used GCN for has worked well. Okay, so yeah, that's it for the video. Next, we will try to cover the update of this GCN, which is nothing but the GAT, Graph Attention Network, right? And then we'll see how that spans out and how it is different from GCN, right? For now, thank you so much. Bye bye.